So today we're going to go over a number of examples related to axial load, both determinate and indeterminate. We're going to start with this one where we have a window washer standing out at the edge of the platform. And our question is, what is the amount of deflection that we're going to see at the location of this individual? Downward deflection. Whenever we approach these problems, we want to go through each of the pillars of mechanics and materials, starting with equilibrium. So the number one thing we're going to look at is equilibrium. And if it's a determinate problem, we will be able to calculate the forces in the members directly from equilibrium. If it's not, we'll find that we have too many unknowns, and then we'll move on to our next equation, our next pillar of mechanics and materials, in order to get the necessary equations to solve. So for this one, I would argue that we should implement equilibrium by looking at the moment about some stationary point. So we might say we're going to look at the center of this platform as our reference point. The platform itself has some weight W, and that would be acting at the centroid, correct? So it would be acting here. And of course, the window washer is acting where the window washer is standing. So if we take the sum of the moment about point O, we're going to have a reaction on the left and a reaction on the right. So we'll say our reaction 1 times L over 2, and that's going to give us a negative moment. So negative R1 L over 2. And then we have a similar moment, but positive with R2 times L over 2. We don't have any moment from the platform itself because it's acting through that point, but the window washer gives us a negative moment of F times 3L over 2. So when we solve this, well, actually, we can't solve it yet, right? We have one equation, two unknowns, R1 and R2. So we could also look at the sum of the forces in the y direction. And now we have R1 plus R2 minus W minus F equals 0. And I got a little sloppy. That first equation also has to equal 0. So now we have two equations, two unknowns. And we can solve for R1, which is going to be equal to W over 2 minus F, and R2, which is W over 2 plus 2F. So that's what you get if you solve that system of equations.
What are those EAL?
That's just saying that we have properties E, A, and L for both of them. They have some length, some area, and some modulus elasticity. Yeah. And they're the same for both members. Thank you for asking that. All right, so we were able to solve directly for the forces, which means that this is a determinate problem. So now that we have forces, when we move on to our second step, which is kinematics, and our third step, which is material relations, we're doing it in such a way that we're plugging in our known force. We're not setting up a system of equations, we're just plugging into these equations. So sometimes it's easier to start or to skip to your material relations first, as opposed to going directly to kinematics, just to kind of get this written down, even though it's only meaningful once we put it into our kinematics equation. Sometimes I just like to write this down first. So we can say that, and I take it back, actually, we can calculate this directly in this case because it's determinate. So with del 1, that would be the elongation of rope 1, or the change in length. We know that it's going to be equal to the force in rope 1, which is W over 2 minus F times L over AE. So if we were given A, E, and L, we could calculate that directly. And for del 2, it's going to be W over 2 plus 2F times L over AE. So at this point, we've actually solved this problem directly without looking at our kinematics. So with determinate problems, you'll notice that we really have more equations than is necessary to solve our problem. But we can go ahead and look at our kinematics. If this is our initial setup, we're going to have some deflection. And it's going to be more so towards where the individual is standing. So this is highly exaggerated, but this would be our del 1, del 2, and then del 3 is where the individual was standing. And the way that we're going to relate these is through similar triangles. You know that if this is a rigid platform, that whole thing is going to rotate. So you can look at, say, this triangle, and we can look at that triangle, and because they share an angle, we know that they're going to be, similar triangles. So this leg here is going to be del 2 minus del 1, and this leg over here is del 3 minus del 1. So from similar triangles, if we look at the big triangle, we have del 3 minus del 1 over 2L, right? Because this was L and that was L. That has to be equal to the littler triangle, del 2 minus del 1 over L, which tells us that del 3 is going to be equal to 2 times del 2 minus del 1. So if we were just looking for the elongation in the wires themselves, then steps 1 and 3 together would have given us enough information, right? From equilibrium, we could get the forces. From material relations, we get the elongations. But because we threw in this extra step where we want to know the elongation, or the deflection rather, somewhere else, that's why we, in this case, continued on to the compatibility equations. But really, like I said, for a determinate problem, you would end up using step 2 or step 3. But if it's asking you for this other information, then you might need all 3. Yes?
For the similar triangle, could we not use from like the farmost left point to L1 as our beginning?
So could you use this?
Yeah.
The problem with that is going to be that you don't know this displacement of this end. You don't know where that goes. All we know are the displacements of the 2 ropes. Yes?
I get how we said del 2 minus del 1 is those like little pieces, and del 3 minus del 1, but what did you do when you put those in like a fraction?
So, okay, so similar triangle is you take two sides of a triangle and divide one or the other, and that ratio has to be the same between the two similar triangles. So I could have done over the hypotenuse and it would have been the same, but I'm taking essentially the vertical leg over the horizontal leg of this triangle of the big one and saying that has to be equal to the vertical over the horizontal leg of the smaller triangle.
And that just gave you that final equation?
Yes, it reduces to that.
But you already have those values, right? Del 3, del 2, del 1?
We have del 1 and del 2 from our material relations. Yes, so we can plug those in here. And we see that this is 2 times del 2. Let's see, del 2 was W over 2 minus F times L over AE minus W over 2 plus 2F times L over AE. Oops. I don't think this 2 belongs here, right? I need to erase that. Okay. And then that becomes your solution. So then if you wanted to know for what weight F, so what weight of an individual does this platform become unstable? How might you approach that question? If I want to know for what weight of an individual is this platform unstable? Maybe first tell me what would make this unstable.
Going fast.
Yes. Yes, but only indirectly. That leads to something else.
That's the elastic.
Possibly. So maybe now you have a lot of deflection because it's in the elastic region.
The tension of R1 is less.
Yes. So if we go from R1 being tension to R1 being compression, so if this is, say, a rope and you try to put that into compression, you now have nothing to resist that. And so now you're going to tip your platform over, right? That would be where you become unstable. And that's related to the rotation. If you get enough rotation, it no longer is tension and it starts to become wanting to be compression. But if there's nothing to resist that compression, it'll just flip. It's no longer in equilibrium. So to do that, we can go back and look at our equation for the force, for the reaction. So you can see here the answer is that when this force becomes greater than half of your platform, you're no longer going to be able to have a stable condition when the individual is out at the end. Okay. So these are things that you'd be thinking about if you were the engineer designing this platform, and you'd always have some rating that says, you know, do not occupy with more than so many pounds, and you would want to think to yourself, where's the worst place I could put that weight to, right? Or maybe you have some warning that says do not go beyond this point, but that's not, you know how people deal with that, right? Yeah. Yeah. All right, so another example. This one is indeterminate. We have 2 different materials fixed on the left and right hand side, and at the interface in between the materials, we're applying a load 2 times P. So some axial load. When you have problems like this, you can draw free body diagrams. So you can take a cut on the left and the right hand side of that load application, and you're going to end up with 3 different diagrams. You have your load applied here at the middle, and you have you're going to have reactions. So it's up to you which direction you want to show these force arrows. There's kind of 2 different ways. We could just draw them both in the positive direction. And then you can look at this and see that obviously one of those or both of those is wrong, correct? We can't have our force applied and our 2 reactions all pointing in the same direction. least not in statics. Right? Or if we want it to be in static equilibrium, we can't have this. So you can either draw them all in the positive direction and then later find out that they're going to be, one of them is going to be negative, which would mean that it would be compression. Or you can preemptively, by inspection, determine which one's going to be compression and which one's going to be tension, right? Because if I'm pulling on that to the right, member 2, the one that's on the right-hand side, is going to have to be shrinking, and which means it's going to be in compression. The one on the left-hand side would be put into tension. It would be expanding. Do you have a preference how we do this? No? No. All right. Then, in absence of your preference, I'll go ahead and I'll just say this one is compression. This one is tension. Having second thoughts. I kid, let's not. Let's put them both. So I should also go back and retract what I just said. I misspoke when I said point them both to the right. The default is putting them both in tension, right? When we've taken section cuts in the past, the default is we draw them in tension. So that's our option 1, is show everything in tension. Option 2 is put it in tension or compression based on what it actually is. So I'm going to go ahead and put them both in tension, which I know is wrong, but I'll do it anyway. So if you follow that through, this is what your diagrams look like. So when it comes to equilibrium, we could write an equilibrium statement for any of these 3, but only one is useful. Which one is useful to us? The middle one? All right, good call. All right, the problem with the left one and the right one is that you just get F1 equals F1 or F2 equals F2, and that doesn't do a whole lot for us. But in the middle, we have things interacting. So here we could say negative F1 plus 2P plus F2 has to equal 0. And if in the end of all this, we end up getting a negative number, that means that we assumed the wrong direction for our force, that it wasn't actually in tension. In the previous example, we made 2 equations. We made an axial force equation and we made a moment equation. And that's how we ended up solving for those 2 variables. But in this case, we're not able to do that, right? There's no point along this member where I can take the moment about it and get anything back, because all these forces are collinear. And so there's no way to get meaningful information about a moment equation. So instead, we need to invoke the next pillar of mechanics of materials. And that would be kinematics. So at this point, it's important that you're consistent with your sign conventions here. So we assumed tension for both of those. So we're now going to assume expansion for both of these. So we're going to say that del 1 plus del 2. So we're imagining that both of these are getting larger. But we know that the sum has to equal 0. So you can see right there, when this finally gets solved, one of those is going to have to be a negative value in order for this to work out, which will coincide with that negative force that we're going to solve for. Yes?
What did it help us to cut it and put those reactions? Not reaction, but
Why did it help us?
Yeah, how do we use that?
You use that to get your equilibrium statement. So this picture helped us get that equation.
So we got that from the motion.
Yeah. Okay, and then we know that as these both expand or both change shape, that has to sum to 0. Then our material relations is what's going to bring this all together. Right now we have an equilibrium statement, which involves our forces. We have a kinematic statement, which involves our displacements. Material relations is what relates the forces and the displacements together. So then we come here and we say that, so for material relations, we know that individually, each of these del 1s and del 2s is equal to PL over AE, where, of course, you use the values pertaining to the member. So we have P1 L1 over A1 E1, and same thing for member 2, P2 L2 over A2 E2. And then we can plug those in to our kinematics relations. So at this point, we have these 4 equations, and we're going to solve the system. So the way we do that is by plugging these into the kinematics equations. So this goes here, that goes there. And we get P1 L1 over A1 E1. You know what? I need to be more consistent with my nomenclature. I'm sorry. These should be Fs. And we know that has to equal 0. So now we have our equilibrium equation that is a function of F1 and F2, and our kinematics and material relations that have been combined into one equation that is also a function of F1 and F2, and we can solve for those values of F1 and F2. Any questions about that procedure? So the main difference between the determinate and the indeterminate problems is that in the determinate problems, you can solve directly in your equilibrium step for your forces, and then if you want to know your displacements, you plug them directly in. Probably the easiest place to plug them is into this material relations. Whereas if you have an indeterminate problem, which means you cannot solve your equilibrium statements directly, you then need to write out your kinematics and your material equations and get a system that you can eventually solve, like this system here where you'd solve for F1 and F2. Now, when you do finally solve this, you're going to see that F1 is going to be positive, which would indicate that this side here is in tension. And then F2 is going to be negative, which would indicate that that side is in compression. And then that the fact that F2 is negative would then propagate down into this equation and would give you a negative del 2, meaning that it is going to be getting shorter. Yes.
You said we could not just have it in tension, right? We could.
Yes.
Okay.
Yeah, so what you can do is you can say, well, at this interface, oh, I didn't do there. If I have 2p, like that, I can say, I know some of that is going to be resisted by this member and some of it's going to be resisted by that member. And you kind of, you know the way that these have to act. You can imagine to yourself, say this one doesn't provide any resistance, then the full resistance comes from the right-hand side and has to be to the left. same story. If the right-hand member didn't provide any resistance, it would all be from the left-hand side, and it would also be to the left. So therefore, when they act together, they're going to each provide some of that resistance, and it's going to be in the same direction that they would if they were working individually. So you can start here. So if you do that, then your equilibrium equation is slightly different. Your equilibrium equation, if this is F1 and this is F2, becomes negative F1 minus F2 plus 2p equals 0. So now what you're doing is you're preemptively putting this negative sign here. That means you're going to get a positive F2 out of this system. But your overall, the equation is essentially the same. It's just you're pulling that negative sign out, explicitly accounting for it here. And then because you're going to get a positive F2, that means that when you write your material relations equation like this, you're also going to get a positive del, right? Positive F2 will lead you to a positive del, but you know that's not the case. You know that del needs to be negative. So you need to also account for it in your kinematics equation. What's going to end up happening is you have del 1 minus del 2, because you know that del 2 is going to be compression, but it's going to be expressed as a positive number, equals 0. So probably like the best way in order to avoid mistakes is probably to always just assume tension and then let the negative signs tell you what's what. But once you get intuition to know what the outcome is going to be, you can use dels and f's as their absolute value all the time, and then put the negative sign in the equation where it belongs to indicate contraction or equilibrium, meaning going to the left. All right, so now we have this example. These always seem to be slightly more challenging when we're dealing with relative rotation or relative movement instead of some absolute fixed point. But here we have a nut. I brought, I'm not sure that this does a whole lot for you, but here's a nut on a bolt. So when I turn this all the way around, so if I take this face and I turn it 360 degrees, now it's back towards you, it actually moved upward on the bolt. And the amount of that upward movement has to do with the orientation of these threads. The more inclined the threads are, the more that nut is going to move up the bolt for each turn. So in this particular problem, I'm saying that I have this situation where I have a sleeve, an aluminum sleeve on a steel bolt. So it's kind of like this. You can imagine that these washers create a sleeve. And I'm saying that I got it so that it was just snug. So it's just, there's no extra space in there. And then I continued to turn it a quarter of a turn. And that extra quarter of a turn, well, see, for each full turn, did I put it on there? And that advances a quarter turn. No, I didn't put the relevant information about the threads on there. So some information that you need to know is that the nut advances 0.06 inches per turn. So that's based on the threads. Each time I turn it 360 degrees, the nut moves relative to the bolt 0.06 inches. So if I have it just snug and then I turn it another quarter turn, the first thing I want to figure out is how much vertically does that nut have to move relative to the bolt in order to make that turn. So if it's 0.06 for a full turn, then a quarter turn is going to be 1/4 times 0.06, which is going to give us 0.015 inches. That's how much it's moving. All right. Now we're going to start with our equilibrium. So we always like to start with equilibrium. if this was snug and I turn the nut, there's one of two things that can happen, and reality is it's a combination of both. In order for the nut to advance onto higher on the bolt, one option is this bolt could be pulled in tension downward, right? If this shell is not going to give, that means that the bolt is actually being pulled downward with the rigid shell remaining around it. Or the other option is that the bolt is staying in place and you're compressing this shell in order to get the nut to advance. Would you agree that those are my two extreme cases? Okay, so I either have my bolt in tension or my shell in compression. And the reality of the situation is it's a little bit of both. Right? As long as one of those is not infinitely rigid, you're going to end up with both. So what that's going to look like is if I have this shell around, that nut advancing is going to put compression into that shell. And equal and opposite tells us that if I have that bolt with the nut around it, you're going to have equal and opposite reactions, which are then going to put that bolt into tension.
What is the first picture?
That's the shell, the sleeve that's going around. So I'm looking at more or less a cross section of it. In this problem, I'm going to go ahead and make the assumption that this is compression and this is tension, and I'm going to use positive values for each. So my equilibrium equation is that my tension in my bolt, so the force F, we'll call it FST for force in the steel, minus the force in the aluminum. I say minus because I know it's going to be a compressive force, but I want to use an absolute value of that force, has to equal 0. Or another way that I can write that is that FST is equal to FAL. Okay? Equilibrium, everything has to be, these two forces have to be equal. So I figured that out, but I don't actually know the magnitude, and I can't know the magnitude because I don't have another equilibrium equation. I have nothing to take the moment about because these are two kind of collinear forces. So I have no choice but to move on to my next pillar of mechanics and materials, which is kinematics.
That's steel and aluminum. The ST and the AL.
Yes, steel and aluminum, yeah. So number 2 is kinematics. So this is looking at how these objects are moving relative to each other. I know that the bolt has to, or I should say the nut has to move 0.015 inches relative to the bolt. So that bolt is going to extend down. We're gonna look at our downward as our positive. So that we're gonna look at this as the bolt is, the threads of the bolt are moving downward 0.015 inches relative to that nut. And in terms of getting this equation, personally, I think that the easiest way to do it is to look at your two extremes and look at how that would look. So for example, if this were entirely the if the sleeve were staying rigid and it was just this bolt and that was elongating, then I would say that the elongation in that steel of that bolt had to be equal to that full 1.5 inches, right? And on the contrary, if this bolt were rigid and we were looking at just the sleeve compressing, but the fact that it's compressing, I'd put a negative sign there because my elongation is going to be positive because I assumed a positive value for the force. So I'd say that negative elongation would have to give me that full 0.015 inches. But the reality is that neither one is rigid. So it's a combination of these two, which means the reality is that the delta of the steel minus the delta of the aluminum has to together equal that 0.015 relative motion. So it's either my bolt elongating or my sleeve contracting, or a combination of the two. And then the third step is always our material relations. So we know that for both of our materials, both aluminum and steel, we can say that the force times the length over the EA values gives us our elongation. So the force of our steel, I'm just using a single L variable because they both have the same length. And at this point, we've written out all of our equations and we should be able to solve. Yes. Okay, so if we want to plug these in, remember we're plugging them into the equation that said the elongation of the steel minus that contraction of the aluminum equaled 0.015. So we're going to plug these in here. So this is going to say that the force in the steel, and at this point, I might remind you of our equilibrium equation. What did our equilibrium equation say? Okay, which is also like saying that they're equal each other. So I'm going to drop the subscript on my F's and just let them both be F. So we have FL over E steel, A steel, minus FL over E aluminum, A aluminum, equals 0.015. And the question was asking us, what is the force in the bolt? Okay. Yeah, find the tension in the bolt. So in this case, it's going to be the same as the compression in the sleeve. So we solve for F, which is 0.015 divided by L times 1 over E steel, A steel, minus 1 over E aluminum, A aluminum. Then we can plug in values from the problem. Okay, so E steel, typically 29,000 KSI. Area of steel was given in the problem. It was given as 0.11 inches squared. E aluminum, We're going to use 10,000 KSI in this problem. Actually, I take it back. No, 10,600. I believe 10,600 is the value that's given in your textbook. You often see just 10,000 used as well. So we're going to use that. And then the aluminum had a 0.5 inches squared. So you plug each of those values in, and the answer that you're going to get is 40 kips. So 40,000 pounds. So suffice to say, I cannot do that with my fingers. Once it's snug, I have a very hard time twisting it any farther without the use of some pretty strong tools.
What's our L? 3 inches?
Oh, thank you. Yeah, that should be 3 inches. And so if you want to know how much the steel is elongating or how much the sleeve is contracting, you would then plug this 40 kip force back in to these equations. So the other thing we could look at is, well, say, what if this sleeve were rigid? What if this sleeve were not aluminum, but some material that relative to steel is rigid? And then how would that affect the force in this bolt?
So then it would have been only
That follows, which is equal, place one of them will equal 0.15.
so one of those fractions.
Right. This one, right? The aluminum.
The one that you don't want.
Yeah. Because you'd have an infinite, you get rigidity by having an infinite E value. So you plug infinity in there, and then that fraction becomes 0, and then you could solve your problem that way as well.
Then wouldn't the steel be? Will that cancel?
The sleeve is the aluminum, and we're saying that that is the rigid in that scenario. All right. So similar to the other problem, this is one way to solve it. The other way would be to, instead of assuming compression and tension, is to keep it real general, where your equilibrium statement would be that the F in the aluminum plus the F in the steel equals 0, and you're going to let that negative sign come into your final solution to tell you whether it's compression or tension. But if you do that, then you have to leave your elongation statement real general, because you have to let that also be governed by your solution, as opposed to up here where we forced this aluminum to be contracting through that negative sign. Cool. All right. Okay, so this slide actually sends us to a whole different PowerPoint. Okay, so just looking at how we could apply this to an indeterminate truss example. So when you're in statics and you had trusses, you typically only had 2 members coming together at a point. So you could solve with your sum of the forces in the X, sum of the forces in the Y, what the forces in those members would be. But if you have, say, 3 members coming together at a point, that no longer works. You can't take the moment because all 3 points are passing through the same point A, and so you can't solve, you don't have 3 equations to solve for these 3 forces. But what you do know is that there's mechanics and materials to help us. So we can look at kinematics and we can look at material relations. So our equilibrium is the same as it ever was. You set up your system of equations, and so you would have your sum of the forces in the x, sum of the forces in the y. So that would give you these two equations, and they're of course going to be functions of the angle of these members. And then we have compatibility. Compatibility, we need to look at, I know you didn't have time to write that down. I'm sorry. So compatibility, we're looking at how point A moves. And we know that as point A moves, all of those wires are going to move with it. And so there's some U and V that tells us the displacement of point A. So some horizontal and some vertical displacement. And we can express that in terms of the elongations of these members. So from Pythagorean theorem, if we have some initial length, so if this is our initial member, we have some initial length that's quantified based on Pythagorean theorem, where x1 and x2 and y1 and y2 are the x and y components of points 1 and 2. Would you agree that can be done? Okay, so then we're going to move it. We're going to move each end by u and v, and each end can move independent of the other, so they can each have their own u and v values. And then we get our final length. So this, let's say green color here is our final length. And so I'll call that L plus del. So the initial length plus how much it elongates, quantity squared. I can use Pythagorean theorem based on my new coordinate system. And that would look like this. So it's my initial coordinates plus how much they moved. And then I just move little terms around to get all my x's together and my u's together. Then on this next slide, so this is the equation I had on the previous slide. This next slide, I'm arguing that if I use my foiling, and I FOIL this out, I'm going to get this equation here. So I know that has to be equal to all of this stuff that I had here. And now I can say that L squared, remember a couple slides ago, I showed you what L squared was equal to. Well, that happens to be, this here happens to be equal to L, right? That's what we talked about 2 slides ago. Pythagorean theorem gave us that was equal to L. I'm going to say that del squared is really, really tiny, and del squared is going to be these terms, which are essentially 0. So I'm going to get rid of those, and what I'm left with is this stuff here in the middle, and it has to be equal to my 2L del. From that, so I'll repeat that equation at the top of this slide. That 2 can get deleted from each term. I know that x2 minus x1 over L is the same thing as calculating cosine of theta. And I know y2 minus y1 over L is the same thing as sine theta. Therefore, I can plug those in for this over L and that over L. And I get that this del is then equal to u2 minus u1 cosine theta, v2 minus v1 sine theta. So we can do a real quick, I know I went really fast, it's because I don't really care that you memorize all those steps. This is just a derivation. What I want you to remember is this equation here. This relates, this elongation of the member is related to what movements its ends have. And so if you look at, say, a member that's in the x direction, and this is L, and this is, say, my delta x, so I extend it. Let's say that this point has u1 equals delta x, and I guess this would be point 2. u2 equals delta x, and v2 equals 0. This one has u and v equal to 0. Okay, so my left hand end isn't moving, my right hand is moving to the right by some delta x. That means that my U1 and V1 are 0. Theta is measured from the x-axis. So in this case, theta would be 0, which means sine of 0 is 0, so that whole term goes away. And what I'm left with is that the elongation is equal to U2, which is delta x, times cosine theta, which is 1. So my entire elongation is just that delta x that I told you it moved. So you're always really using this equation, you just don't realize it. Right? The default case of elongation being how much it moved in the axial direction is a simplification of this formula. Okay, so now that you agree that del is a function of the endpoint displacements, we can go in and we can write this equation for all 3 of those ropes. Each of those ropes has some elongation that is going to be a function of how much its ends move. So I can pick, say, these stationary points to be my point 1, end 1, and those are all fixed, or at least translation-wise they're fixed. And then point 2, they all share. So that means that in these 3 equations, U2 and V2 are all going to be the same in each equation. Right? It's just however much that point is moving, which might be a variable for now, and then we'll solve for it later. And then U1 and V1 are always going to be 0 in this particular setup because my 1s have all been pinned. If I had, say, a support that was slipping, so it was, say, settling as this was being applied, then it would no longer be 0. I'd have some number there for how much it settled. Then my angles are going to come, I take a line pointed in the x direction starting at node 1. It's really important that you start at node 1. So at node 1, I take an x angle, and then I'm going to measure the angle until I get to the rope. And so in this case, it's 30 degrees. And it's negative because a positive angle would be counterclockwise. In this case, it's, whoops, I don't want to do that. In this case, it's negative 90. And in this case, it is negative 120. So then you get these 3 different equations for your elongations. That's kinematics. And then material relations, each of those is equal to FL over AE. The only reason that they look different here is because I defined this as my length, which means that I can use these triangles to get, say, LAD and LAB, but they're all going to be functions of that dimension that I've defined as my length. And that gives me 8 equations. So the important thing is equilibrium. Gives you 2 equations. Material relations gives you 3 equations. And then that equation that I derived very quickly gives you 3 more. That's your kinematics. Cool. All right. Okay, last thing. I'll go back here. There. This didn't get, I made some changes to this before class that didn't get incorporated. Okay, so in-class assignment, for the last 10 minutes, I want you to think through this. That's okay, we'll do it as is. So I'm not giving you any, I'm not telling you what these materials are, but you can presume that they're different materials, which means that each of them is going to have a unique E and alpha value, alpha being your thermal coefficient. Presumably they could each have a unique length and unique area. And the question is to find the delta T. So how much is the temperature going to increase by such that the force generated is negative 200 newtons? So first, this is going to extend freely due to the temperature increase. At some point, it's going to come into contact with that side. And we know that it is actually, the temperature is actually increased beyond that because we're now developing compression. And so you could calculate some temperature to get it to just barely touch, or you could calculate some temperature to actually develop compression. So you can assume that this is extended all the way to that side, and the temperature is still increasing. See if you can set that up. And if you need help, let me know.